Hi and good day everyone. In this video, I will discuss to you the Module 7 in MC-MATH 106, Calculus 1 with Analytic Geometry. But before I start, I would like to introduce myself first. My name is Arnel Silva Jr. I am a second-year college student from Calabanga Community College, taking Bachelor of Secondary Education major in Mathematics. Let's start. The title of Module 7 or the Module 7 is all about one-sided limits and infinite limits. Let's discuss first the one-sided limits. This graph shows the behavior of three different functions around x equals 2. So in letter A, we have f of x is equal to x raised to 2 minus 4 over x minus 2. In letter B, we have g of x is equals to absolute value of x minus 2 over x minus 2. In letter C, we have h of x is equals to 1 over the quantity of x minus 2 raised to 2, sometimes indicating that the limit of a function fails to exist at a point does not provide us with enough information about the behavior of the function at that particular point. To see this, take a look the function g of x equals the absolute value of x minus 2 over the quantity of x minus 2. So here, letter B. As we pick values of x close to 2, g of x does not approach a single value. So the limit as x approaches 2 does not exist. That is, the limit as x approaches 2 of g of x is DNE or does not exist. However, this statement alone does not give us complete picture of the behavior of the function around x value 2. To provide more accurate description, we introduce the idea of one-sided limit. For all values to the left 2 or the negative side of 2, g of x is equals to negative 1. Thus, as x approaches 2 from the left, g of x approaches negative 1. Mathematically, we say that the limit as x approaches 2 from left is 1. So we can write or express this idea as this. The limit as x approaches 2 from the left is negative 1. Similarly, as x approaches 2 from the right or from the positive side, g of x approaches 1. Symbolically, we express or we can write this idea as the limit as x approaches 2 from the right or the positive side is 1. We can now present an informal definition of one-sided limits. So we have two types of one-sided limits. We have limit from the left and the limit from the right. So let's discuss first the limit from the left. Let f of x be function defined at all values in open interval of the form CA and let L be a real number. If the values of the function f of x approach the real L, as the values of x where x is less than a approach the number a, then we say that L is the limit of f of x as x approaches from the left. Symbolically, we can express this idea or we can write this idea as this. The limits as x approaches a from the left of f of x is L. So, in the limit from the left, the value of x is less than, or the value of all x is less than the a. So next one is the limit from the right. Let f of x be a function defined at all values in an open interval of the form AC, and let L be a real number. If the values of the function f of x approach the real number L as the values of x, where x is greater than a approach the number a, then we say that L is the limit of f of x as approach from the right. Symbolically, we can express or write this idea as this. The limits as x approaches a from the right of f of x is equal to L. So all the value of x is coming from the right or greater than, or the value of x is greater than a. Let's have the example 7.1, evaluating one-sided limits, where the function f of x is equal to x plus 1 if x is less than 2, x raised to 2 minus 4 if x is greater than or equal to 2. Evaluate each of the following limits. In letter A, the limit as x approach 2 from the left of f of x. In letter B, we have the limit as x approaches 2 from the right of f of x. So the solution, we can use table of functional values again. Table 7.1, observe that for values of x less than 2, we use f of x is equal to x plus 1, and for the values of x than 2, we use f of x is equal to x raised to 2 minus 4. So on the first table, we use these are the values of x, wherein the values are less than 2, and the functions, we use this function, the f of x is equal to x plus 1, and we need to substitute all the values of x here at f of x is equal to x plus 1 and solve it. In 1.9 we have 2.9, in 1.99 we have 2.99, in 1.999 we have 2.999, and 1.9999 we have 2.9999, and to the last we have 1.99999 we have 2.9999. So on the second table, we have the values, or the value of x are greater than 2, and we need to substitute all the values here in the function f of x is equal to x raised to 2 minus 4 and solve it. So the table of functional values for f of x is equal to x plus 1 if x is less than 2, and x raised to 2 minus 4 if x is greater than or equal to 2. The next, based on this table, we can conclude that a, that limit as x approaches 2 from the left of f of x is equal to 3, and b, the limits, or the limit as x approaches 2 from the right of f of x is equal to 0. Therefore, the two-sided limit of f of x does not exist at x equals 2. So the figure 7.2 shows the graph of f of x and reinforces our conclusion about these limits. So here is the graph. The graph of f of x equal to x plus 1 if x is less than 2, and x raised to 2 minus 4 if x is greater than or equal to 2 has a break at x equals to 2 or equal to 2. Let us now consider the relationship between the limit of function at a point and the limit from the right and left at that point. It seems clear that if the limit from the right and limit from the left have common value, then the common value is the limit of the function at the point. Similarly, if the limit from the left and limit from the right take different values, the limit of the function does not exist. These conclusions are summarized in relating one-sided and two-sided limits. So the theorem 7.1 relating one-sided and two-sided limits. Let f of x be a function defined at all values in open interval containing a with a possible exception of itself, and let L be the real number. Then the limit as x approaches a of f of x is equal to L if and only if limit as x approaches a from the left of f of x is equals to L, and limit as x approaches a from the right of f of x is equal to L. So let us proceed and discuss the infinite limits. Infinite limits, evaluating the limit of a function at a point, or evaluating the limit of a function from the right and left at a point, help us to characterize the behavior of function around given value. As well as we shall see, we can also describe the behavior of functions that do not have infinite limits. We now turn our attention to h of x is equal to 1 over the quantity of x minus 2 raised to 2, the third and final function introduced at the beginning of this section on the figure 7.1. From it graph, we see that as the value of x approaches 2, the values of h of x is equal to 1 over the quantity of x minus 2 raised to 2 become larger and larger, and in fact become infinite. Mathematically, we say that the limit of h of x as x approaches 2 is positive infinity. Symbolically, we can express this idea, or we can write this idea as this: the limit as x approaches 2 of h of x is equal to positive infinity. More generally, we define infinite limit as follows. Now let us proceed to the three types of infinite limits. The first one is the infinite limit from the left. So if the values of x increase without bound as the value of x, wherein the value of x is less than a, we can write the idea or express the idea by this: the limit as x approaches a from the left of f of x is equal to positive infinity. But if the value of f of x decrease without bound as the values of x, where the value of x is less than a, we can write the idea or express the idea by this: the limit as x approaches a from the left of f of x is equal to negative infinity. To the second type on the second type, we have infinite limits from the right. If the value of x increase without bound as the value of x, wherein the value of x is greater than a, we can express the idea, or we can write the idea by this: the limit as x approaches a from the right of f of x is equal to positive infinity. But if the value of f of x decrease without bound as the value of x, where the value of x is greater than a, we can write this idea or express the idea by this: the limit as x approaches a from the right of f of x is equal to negative infinity. To the last type, two-sided infinite limit. So if the value of f of x decrease without bound as the value of x where x is not equal to a, we can express the idea or write the idea by this: the limit as x approaches a of f of x is equal to positive infinity. But if the value of f of x decrease without bound as the value of x where the x is not equal to a, we can write the idea by this: the limit as x approaches a of f of x is equal to negative infinity. Next, recognizing an infinite limit. So evaluate each of the following limits if possible. Use of a table of functional values and graph f of x is equal to 1 over x to confirm your conclusion. So we in letter A we have the limit as x approaches 0 from the left of 1 over x. In letter B we have the limit as x approaches 0 from positive side or from the right of 1 over x. And C we have the limit as x approaches 0 of 1 over x. So the solution begin by constructing or making a table of functional values. So on the first table, these are the values of x, wherein the value of x is less than 0. So only we need to substitute the all value of x by this to this function and write here the answer. So on the next table we have here the value of x, wherein the value of x is less than 0 but they are positive, while in the first table they are negative. And same process, we need to substitute the value of x here sa 1 over x and write here the answer. So the table of functional values for f of x is equal to 1 over x. Next, in letter A, the table of 1 over x decrease without band as approach 0. From the left, we can conclude that the limit as x approach 0 from the left of 1 over x is negative infinity. In letter B naman, the values of 1 over x increase without band as x approaches 0 from the right. We can conclude that the limit as x approaches 0 from the right of 1 over x is equal to positive infinity. So in letter C, we have the limit as x approaches 0 of 1 from the left of 1 over x is equal to negative infinity, and limit as x approaches 0 from the right of 1 over x is equal to positive infinity have different values. We conclude that the limit as x approaches 0 of 1 over x is DNE or does not exist. So the graph of f of x is equal to 1 over x confirms that the limit as x approaches 0 does not exist. So here's the graph. The function of f of x is equal to 1 over x. The quantity of x minus a raised to n has infinite limits at a. So here, in the first graph, the f of x is equal to 1 over the quantity of x minus a raised to n if n is an odd positive number. In the second graph naman, f of x is equal to 1 over x minus a raised to n if n is an even positive integer. So theorem 7.2, infinite limits of positive from the positive integers. If n is a positive even integer, then the limit as x approaches a of 1 over x minus a raised to n is equal to positive infinity. If n is a positive odd integer, then the limit as x approaches a from the right of 1 over x minus a raised to n is equal to positive infinity, and the limit as x approaches a from the left of 1 over x minus a raised to n is equal to negative infinity. We should also point out that the graph of f of x is equal to 1 over the quantity of x minus a 1 over the quantity of x minus a raised to n points on the graph having x coordinates very close to the vertical line. X is equal to a. That is, as x approaches a, the point on the graph f of x are closer to the line x is equal to a. The line x is equal to a is called a vertical asymptote of the graph. We formally define vertical asymptote as follows. So definition, let f of x be a function if any of the following condition hold, then the line x is equal to a is a vertical asymptote of f of x. So here, the limit as x approaches a from the left of f of x is equal to positive infinity or negative infinity. So same lang. No. The limit as x approaches a from the right of f of x is equal to positive infinity or negative infinity. Here, the limit as x approaches a from the f of x is equal to positive or negative infinity. So finding the asymptote, the vertical asymptote. So evaluate each of the following limits using infinite limits from integers. Identify any vertical asymptotes of function f of x is equal to 1 over x plus 3 raised to 4. In letter A, we have the limit as x approaches negative 3 from the left of 1 over the quantity of x plus 3 raised to 4. The solution by using the infinite limits positive integer is the positive infinity. In letter B, we have the limit as x approaches negative 3 from positive side or from the right of 1 over x plus 3 raised to 4. We have the positive infinity. In letter C, the limit as x approaches negative 3 of 1 over x plus 3 raised to 4. The solution by using infinite limits from positive integers is positive infinity. So the function f of x is equal to 1 over the x plus 3 raised to 4 has vertical asymptote of x is equal to negative 3. So example 7.4, behavior of a function at different points. Use the graph of f of x in figure 7.1 to determine each of the following values. The limit as x approaches negative 4 from the left of f of x. The limit of f of x. The limit as x approaches negative 4 from the right of f of x. The limit as x approaches negative 4 of f of x and f of negative 4. So the graph shows of f of x here. Using the infinite limits from positive integer and the graph for reference, we arrive at the following values. So in letter A, we have 0. In letter B is undefined. In letter C we have 6. And letter D we have undefined.